and I'll try to show how this formula came up. So let's say if we have a set that is A, and we are obtaining a relation on A cross A. So if we are asked about how many total number of relations are possible, let's say the cardinality of A is n. So if we ask for all these n entries in A, how many type of relations can be there? So for doing a relation for each element, let's say 1, 2, 3, 4, and so on up to n, we can see that if whether this can be present, either it can be present or it cannot be present. So this element can be present in the relation or cannot be present. So there are two possibilities of this, right? Similarly, for this also there are two possibilities, for this two possibilities, and so on up to this it is two possibilities. But this is only for one relation, that is for mode A. But in the relation, we have seen that there is an ordered pair A cross B, where A will be belonging to A and B also belonging to A, because we are taking the ordered pair on cross product of A cross A. So we need to know that for A cross A, the total number of elements in A cross A is n square. N for this and n for this. So all together we have n square. Like if we have elements in A like 1, 2, and if we have A cross, we are doing A cross A, or we are making a relation on A cross A. So the total number of elements present in A cross A will be 1, 1, 1, 2, and 2, 1, and 2, 2, like that. So all together it is 4, right? So that is why A cross A is n square. Okay, now if we are asked about the total number of relation in A cross A, so we will be taking off like this. So altogether we have n square element. So for any relation, we need to see whether this ordered pair is present or not. Like for 1, 2, 3, 4, 5, 6, and so on up to n square. So there will be n square combination, and we will see that whether this combination is present or not. So there are two possibility whether it is present or it is absent. So total number of relation, if we define in A cross A, can be 2 raised to the power n square. Okay, right. So this is the very first result, and it is very easy. Either this ordered pair can be present or it cannot be present, right? So if all together we have n square ordered pair, so we can just find if it is present in the relation or it cannot be present. So very easy. Second is it's as easy like number of reflexive relation on R. So, reflexive relation means that if we are defining a reflexive relation on A, then for every element in A, AA should be present. Okay, so for every element in A, so let's say all together in the relation we have 1, 2, 3, and so on up to n square element. Now out of this, how many AA combination will be there? Like both symmetric condition will be there. So it will be altogether n, because if we define A equal to 1 and 2, so if we define reflexive relation on A, so it will be either 1, 1 and 1, 2, 2, 2, right? So altogether it's equal to the number of elements in A, right? So number of elements in A is n. So for n entries, let's say for these n entries, it has to be present. So there is only one possibility, because we need these n entries like 1, 1, 2, 2, 3, 3 to be present for this relation to be reflexive. But for the remaining one, that is n square minus n, it will be having two possibilities. It could be present or it couldn't be present. So for n we have one possibility that it should be present, and for these we have two possibility. So we can write 1 raised to the power n into 2 raised to the power n square minus n. Okay, so this is nothing but 1 only. So it is equal to 2 raised to the power n into n minus 1. Okay, because for these remaining n square minus 2 there can be two possibilities. So 2 into 2 into 2 up to how many times n square minus n. So if we define the total number of reflexive relations on A, it is 2 raised to the power n minus 1. Okay, is that clear? Right. So we can check, even if you don't remember the formula for this, you can check from here. Okay. The very third part is number of irreflexive relations on R. Number of irreflexive relations on A. Again, it's the same condition for irreflexive. We don't want this AA pair. So for if altogether it is n square element, so out of this for n element, we want that it shouldn't be present. So the only possibility is one. So it shouldn't be present. This shouldn't be present. This shouldn't be present. Altogether one. So it is 1 raised to the power n. And for the remaining n square minus n elements, it can be present or it cannot be present. So there are two possibilities. So if we are to find the number of irreflexive relation on R, so it will be 2 raised to the power n square minus n, or simply 2 raised to the power n into n minus 1. Okay, so this is the same for reflexive and irreflexive. Okay. Then the third point is number of symmetric relation on R. Now this is something you need to think of, because when we talk of symmetric relation, we say that if AB is present in R, then BA has to be present. Okay, so if we take this total n square elements, right, n square element, so if AB is present, like if we take 1 2, okay, like we took 1 2, so if 1 2 is present, then 2 1 has to be present. So dependency of this to be here depends on to this, right? For other 1 1 2 2, it's fine, right? If it is present, it can be present or it cannot be present, we don't mind. But if we are just choosing things like this, 1 2 2 1, sorry, 1 2, then 3 4, like this, then definitely its opposite has to be present for that. Okay, so first let's take that 1 1 pair, 2 2 pair, how many it will be, like n. So for n we have a possibility that it can be present or it cannot be present for n elements. For the remaining n square minus n, we can have the possibility, like if this is present, this has to be present, like that. Okay, if 3 4 is present, 4 3 has to be present. So the dependency, from this dependency, it will be having the possibility it can be present or it cannot be present. But for this, if it is present, then it has to be present, like that. Okay, if it is not present, then we don't require this, like that. It should go like that. I hope I'm able to explain this part. So what happens in this case, that if we talk about the same part, like if you talk about all together n square elements, so for 1 1 2 2 and so up to n, so 1 1 2 2 3 3, like this up to n. Okay, so all this, it can be present, it can be present, it can be present, or it cannot be present, like this. So up to n we have 2 raised to the power n possibility. For the remaining n square minus n element, okay, n square minus n element, so what we have the possibility, that it can be, let's divide it into two half. Okay, let's divide it into two half. So such that first half is containing elements like 1 2, and second half is containing the reverse part. Okay, so this part, n square minus 2, it has to be, it can be present or it cannot be present, right? So n square minus n divide by 2 has the possibility, just a second, it has the possibility of 2, it can be present or it cannot be present. But if it is not present, okay, but for any possibility, let's say if it is present, then the number of possibility of this will be n square minus n by 2, the number of possibility will be 1. Okay, if it is not present, then also it shouldn't be present, right? So we can divide it like that, 2 raised to the power n into 2 raised to the power n square minus n upon 2. Okay, so it will be something like 2 raised to the power n plus n square minus n upon 2. So 2 raised to the power 2n plus n square minus n upon 2. So 2 raised to the power n square plus n by 2, or we can simply write it as 2 raised to the power n into n plus 1 by 2. Okay, so this is the total number of uh, symmetric relations onto R. Okay, so this is how we got. So even if you don't remember this formula of total number of symmetric relation, you can calculate based on your analysis. That's why I'm showing this analysis part to you. Similarly, if we want to calculate the total number of asymmetric relation, okay, so if we want to calculate the total number of asymmetric relation, asymmetric means that if AB is present, then definitely BA shouldn't be present. Okay. If AB is present, BA shouldn't be present. So again, we come to this point that if they are all together n square elements, okay, if they are all together n square elements, then from here, just a second, let me think my laptop battery is down. Switch it on. Okay, so let's say if all together we have n square element, so out of that we will be having some ordered pair like this: 1 1 2 2 3 3 and so on up to n. Okay, so we have some ordered pair of elements like this, right? So for this n pairs, for asymmetric relation, it has not to be present. So there is only one condition: it shouldn't be present. Sorry, I mean, there is only one way it can be in the relation. It shouldn't be in the relation. I'm writing this one, two, three. Just a second. Let me erase this part. Okay. Yep. So the only condition for all these n elements is it shouldn't be present, right? So there is only one choice for that. But for the remaining n square minus n elements, what is the choice? Let's divide it into two halves such that one half n square minus n by 2 and this n square minus n by 2. So let's say this half contains 1 2 and this half contains 2 1. So we are for asymmetric, if this is present, this has not to be present. Okay, so if 1 2 is present, 2 1 shouldn't be present. If 3 4 is present, 4 3 shouldn't be present. Okay, if it is not present, okay, if it is not present, then it can be present, or it cannot be present. It doesn't mean, like, if it is not present, so there are two conditions. Just analyze this way. So let's say 1 2 is present. Okay, so if 1 2 is can be present or cannot be present, there are two possibility. Okay, it can be present, it cannot be present. But if it is not present, if it is not there into this list, then for this it can be present or cannot be present, right? So for if it is present, so like for if present, then this part can be present. Okay, if it is present, then not present, this shouldn't be present. Okay, because if 1 2 is present, 2 1 shouldn't be present. But if it is not present, let's say in the relation it is not present, then it can be present or it cannot be present. Okay, like this way. So all together if we say, so this is very tedious to understand, but we can understand this from this diagram. I think I drawed it right way only, but let's understand from this part that if for this n square minus 2 elements, there are two possibilities. So let's calculate all together. So for these n elements, 1 raised to the power n into, now for this n square minus n by 2, there are two possibilities. So 2 raised to the power n square minus n by 2. And for each of these possibility, for remaining n square minus n by 2, for if it is present, if this element is present, then it shouldn't be present. Uh, Just a second. If this element is present, like 1 2 is present, then the only possibility for remaining that it shouldn't be present. But if it is not present, then it can be present or it cannot be present. So altogether for this possibility, there are three possibilities for the remaining n square minus n by 2. So 3 raised to the power um, n square minus n by 2. Okay, so it will be we shouldn't be like doing like this way. We can do something like mm, 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 mm. Just a second, let me take it this way. We can't take this as together because into in multiplication, because we don't know whether it is present or not. So let me simplify it in the better way. So if we divide like this, okay, so if we divide like this, for one half it can be present, it cannot be present. For this present part, okay, it shouldn't be present. For this not present part, it can be present or cannot be present. So let's divide it in this way, because it is getting a little bit hectic. So let's divide our entire n square elements in this way, that this contains something like 1 1 2 2, so on up to nn. So these are n. For the remaining n square minus n elements, what we will see, we will take the pair. So 1 2 and then 2 1. Okay, then similarly, uh, 1 2 2 1, then 2 1, sorry, 3 1 and 1 3, like this. Okay, so we are taking these pairs. Now for each pair, let's identify the condition of being present, because the presence of this depends upon the presence of this. So we are just taking all together. Okay, so if 1 2 is present, 2 1 shouldn't be present. If 1 2 is not present, 2 1 can be present, right? So there are two possibilities. If 1 2 is present, 2 1 shouldn't be present. If 1 2 is not present, 2 1 can be present. If 1 2 is not present, 2 1 cannot be present. But the other part is not there, like both tick is not there. So there are three possibilities. Similarly for this also there are three possibilities. So this part is n square minus n by 2. Okay, because we have grouped them to as two way. Okay, so this entire part is n squared minus n by 2. Okay, so for n square minus n by 2, we have the possibilities like 3 raised to the power n square minus n by 2. And for this shouldn't be present, so 1 raised to the power n. Okay, so something like the total number of asymmetric relation, we can write it as 3 raised to the power n into n minus 1 by 2. So this is the total number of asymmetric relations on R. Asymmetric relations on R. Okay, I hope it is clear from this, because in the previous case what we were doing, there was a dependency, so we can't just multiply this in this way. Okay, this will be a just a second, this will be a bad decision to be made. So what we have done, we have just grouped the dependent pairs. Okay, so while grouping it, just we divided it by 2, because we have just grouped these two pairs together, and then we are checking their feasibility of being present or not. Okay, so I think this is the better approach. Then the last one, I think the sixth one is anti-symmetric relation. So anti-symmetric means that if AB is present, BA present, then A should be equal to B. Okay, so if we have this condition like there are altogether n square elements in a relation. So for this part, 1 1, 2 2, 3 3 dot dot up to n, either it can be present or it cannot be present. So there are two possibilities, right? We don't require them to be present, but if they are present, it's also fine. Okay, so this is 2 raised to the power n, right? Now for the remaining n squared minus n elements, so if 1 2 is present, right, then definitely 2 1 shouldn't be present, because in this case, uh, if 1 2 is present and 2 1 is present, and 1 is not equal to 2, right? So we have to check this condition like this way, okay? And then 2 1, sorry, 3 1 and 1 3 and so on. So again we are doing what, we are dividing it into pairwise structure, like n square minus n upon 2. And for each pair we are checking that if 1 2 is present, 2 1 shouldn't be present, right? If 1 2 is not present, okay, again 2 1 can be present. If 1 2 is not present, 2 1 cannot be present, it doesn't affect. So there are three choices for that. So altogether if we write, it is 2 raised to the power n into 3 raised to the power n into n minus 1 upon 2. Okay, so this is the total number of anti-symmetric relations on R. Okay, so it I would suggest that don't remember the things, just go with the analysis if it is being asked in questions. And I think altogether we have discussed uh, uh, six factors: total number of relation, reflexive, irreflexive, symmetric, asymmetric, and antisymmetric. So altogether total number of six type of results on this counting part. But we remember that there is also one thing called number of transitive relations on R. So you remember while we were calculating the transitive relation how difficult it was. So there is algorithm, although Warshall's algorithm and so, but there is no as such closed formula for calculating the total number of transitive relations on R. So remember this part in your mind. And the last one is reflexive the number of reflexive and symmetric relation on A. The number of reflexive and symmetric relation on A. So if we want to calculate the total number of reflexive and symmetric relation on A, so we already have total number of reflexive relations. So here we are just guaranteeing that the relation has to be reflexive and symmetric. So again, we can identify like this. So if we have the set for the n elements, like for this pair 1 1 2 2 and so we for being reflexive, it has to be present, like this. Okay, so 1 raised to the power n, and for the remaining n square minus n element, for if 1 2 1 1 2 is present, then 2 1 has not to be present, right? So it has not to be present. So we can divide it like for n square minus n upon 2, there are possibilities, there are choices. Okay, so there are two choices, and for each choice we can define, like if this is present, this shouldn't be present; if this is present, this shouldn't be present. If this is not present, okay, this can be present. Okay, like something like this. So if we have 1 2 and 2 1, so we can write it like if 1 2 is present, 2 1 shouldn't 2 1 should be present. Okay, I'm sorry. If 1 2 is present, 2 1 should be present. If 1 2 is not present, then 2 1 should also be not present. So there are two possibilities. Okay, so 2 raised to the power n square minus n by 2. So this is the total number of reflexive and symmetric relations on A. So I hope from this part some results on counting perspective is clear. So I hope we have covered a lot in relations, like different order pair, inverse relation, composite relation, and various type of relations and their closures, right? So now we will be discussing on to poset and toset stuffs. So that we will check in the next lecture. That's all for this part. So if you do have any comments or question, please do comment in the comment section, and yeah, keep watching. Thank you.